Okay, welcome back. So our next speaker is, well, let me just say, first of all, we're going to have more coffee tomorrow. Addicted like I am, we should have more coffee for the break and for. So our next speaker is Balushi from Berkeley. Thanks, Zach, for coming. And for surviving this crazy travel conditions and some of you speaking. And yeah, so please go ahead.
All right, thanks, JP. Can everyone hear me? Great. So again, my name is Balushi. I'm from UC Berkeley. And so what I'm going to talk about today is actually more of a broader overview of the field in synthesis of these transition metal dichlorogenides. I'll talk about what they are. But just a little bit of background of myself. I'm also a crystal grower, but mostly the things that I've been doing throughout the years are mostly in the area of epitaxy, compound semiconductors, and these layered materials, and some of these quantum materials. And so I've worked across crystal growth in different dimensions, and I continue to do that at Berkeley. But I'd like to talk about a class of materials that I think is very exciting, especially the past 10 years. These are these transition metal dichlorogenides. And for those who are interested in getting more information or new to this field, I really recommend this annual review that we co-wrote on the synthesis of these transition metal dichlorogenides. Also, if you're interested in some of the applied nature of these materials, what are some of the interesting problems in a variety of areas, I would recommend this review that we've also published recently, and then a perspective on what is currently very interesting in this field. And then if you're interested in these slides, I'm happy to give it to you. Just send me an email. More than happy to publish this, even if they're later on. So anytime, just feel free to ask me. So I have a break in the middle of the talk if you have questions, but you can also stop me and ask questions as well. So what are these transition metal dichlorogenides? So essentially, they consist of these transition metals from the periodic table and these chalcogens, typically sulfur, selenium, and tellurium. And so what the structure looks like is essentially you have a transition metal sort of sandwiched between two layers of chalcogen, where you have these transition metals that are interacting with these chalcogen ligands from the top and the bottom. And so they're strongly covalently bonded in plane, where you have weak out of plane bonding, where these layers are essentially held together through electrostatic forces known as van der Waals. And so what's interesting about this class of materials is that you can stabilize monolayers of them, and they remain quite passivated, similar to what people have seen in graphene and boron nitride. And also you can break inversion symmetry. There's some interesting physics that come about being at the monolayer limit. Some of the examples of these materials, you might have heard of things like molybdenum and tungsten disulfide that come up a lot, but there's a lot of interesting other kinds of systems with this MX2 structure, like tantalum, niobium, sulfide, selenide, telluride. These materials have all sorts of interesting physical properties. Some are superconducting, some have interesting logical behavior. So there's a lot of things going on in the system. So what I'd like to first do is to review the crystal structures of this class of materials, okay? So the way to break down the crystal structure is essentially they are hexagonal in nature, and they have some local symmetry differences between the different phases. So the main ones are this H and T phase. Okay, so if you look at the H phase here, you have the transition metal interacting. You have this tetrahedron on both sides, and in the case of this H phase, what happens is that this tetrahedron on the bottom and top are symmetric to each other. This gives rise to this trigonal prismatic phase. Okay. While if you have this 180-degree rotation between the tetrahedron in the top and the bottom, then you have this T phase, which is octahedral. Okay. And another thing you'll notice is that in front of these nomenclatures, there's these numbers, and this is associating with the stacking order. For example, what 2H means, it's AB stacking. But if you look at the top view, it kind of looks like something like graphene or boron nitride, except in this case, we have chalcogen and transition metal sort of alternating in the crystal structure. Okay. So this is the two sort of breakdown in crystal structure, but this T phrase can also be broken down and can also can go from a threefold to twofold symmetry. Okay, essentially what happens is you can get these transition metals to dimerize, and this leads to distortion in the chalcogen outer plane, giving rise to different stacking sequences as well. And so the one T phase breaks down into this T prime and TD phase. Example of the T prime and TD or something like tantalum, tungsten and molybdenum ditelluride. And so the real difference between these two phases is that you have a slight shift in the layers, which changes the angle in the C direction. Okay. Now then you have other stacking. So there's also something called the R3R phase, which is rhombohedral. And so what this essentially is just a different stacking compared to the H phase. And then you have something recently, a lot of people are making crystals that are 4H, which is essentially alternating between the H and T phases. So what is the reason I'm telling you all that this system is rich in phases? It turns out all these stacking orders and different symmetries actually give rise to very unique electronic and optical properties. And a lot of these phases are quite stable, and so you can actually make these crystals from a variety of phases and combine them and do all sorts of interesting physics. So, so a lot of these materials are also just general semiconductors. One of the interesting things that was first seen in this system by Kin Phi Mac and others is that if you take a bulk crystal and you start to thin it down to the monolayer, there's a transition in the band gap from a direct band gap semiconductor, the indirect to a direct band gap at the K point. So this is one of the first things that people have seen. A nice thing about these crystal structures is that you can sort of think about stacking them into a variety of van der Waals heterostructures due to the reduced mismatch requirements. You can also create twisted structures. That's a big thing these days. Another interesting thing is that since the band gap is at the inequivalent K points, due to strong spin orbit coupling, these are due to this the d orbitals, you can essentially split the valence band, and this gives rise to unequal population that gives rise to optical selection rules and value polarization in these materials. So a lot of people are interested in this for electronics. If you compare these transition metal dichalcogenics to conventional semiconductors like gallium arsenide and so forth, actually have very large exciton binding energies in their individual layers, but also they have a variety of band alignments, and you can create like type 2 junctions and give rise to something that's called an interlayer exciton. It's an electron hole pair that are bound between the layers and create excitonic devices that you can modulate, like with strain, for example. Also, because these are atomically thin layers, you have reduced screening effects, and you can modulate the electronic properties by simply just changing the dielectric environment, right? So you can create PN junctions just by lying it on different surfaces that have a different electrostatic effect to the layer. It just changes the exciton and so forth. So lots of interesting things from a semiconductor perspective, but also beyond semiconductors, these materials have other rich physics. Some are superconducting, some are charge density wave materials, some are quantum spin insulators. You have magnetoresistance, Wild phases. Recently combining or stabilizing specific phases, you can get what people think are topological superconductors. So there's just so many things going on in this family, but ultimately to use these materials, right, these different phases in a variety of applications, you usually need to have monolayers of these materials. That's where a lot of the physics come about. And that actually is a different challenge from a synthesis perspective, because now you need to control or form these monolayers and then combine them into more sophisticated hybrid structures. So what I'd like to do is talk about some of the challenges in this field, what people have done, what are sort of the best results out there these days, and then what is the opportunity for you as students that could participate in this field more actively, okay? So there's generally two approaches to ultimately make these applications or kind of study these physics. One is essentially a top-down approach. So there was lots of really lovely talks today about bulk crystal growth. I'll talk about it very briefly. And so essentially you start off with a nice bulk crystal that you can grow by a variety of techniques, and then you essentially thin that down to monolayer. Then there's a second way of doing this, is to start from the bottom up. So a lot of times you can do this using conventional bottom-up techniques, vapor phase and physical vapor deposition techniques. And so I'm going to also touch on these two things. So this particular system, this transition metal dichrocosmetics, is actually a very challenging system to synthesize. And the reason for this is first is that a lot of these transition metal dichrocosmetics do not melt congruently. So a lot of times when you want to make these materials from melt growth methods, even things like directional solidification processes, Bridgman, Tarkovsky, it's actually very challenging to do this. So you ultimately have eliminated a huge, most of these materials are hard to make through these techniques that are very well established. The other thing that's very challenging is now, you have this MX2 structure, right? You have a transition metal, right? We know that transition metals have very high melting points. Then you have chalcogen, they have very high vapor pressure. These are two very different species. You're trying to combine them to ultimately make this MX2 structure. And that's actually very challenging in terms of. And so a lot of times, this is what's the limiting factor and dictates what you can actually make today. So there are different ways of making these materials, and mostly what people have been working on in this field are vapor phase techniques, things like bulk growth by chemical vapor transport. You can also do flux growth. But also in thin film form, mainly the work has been in chemical vapor deposition techniques and by molecular beam epitaxy. Now you could, sputter these things, but they're not very good. But there's also some interesting little tricks that you can play to also get things with it sort of outside of these three categories. I'll talk about that. But just going back to the elements themselves, so if we're going to make these materials, we need to consider that these fluxes that are ultimately allowing you to then grow these materials through these vapor techniques, they have to be sufficient, right? You have to have some sufficient vapor pressure. So, the chalcogens are really great because they have, low melting points relatively and high vapor pressures. And so transport is not an issue at all, okay? But I just said that the transition metals, this is take an example of molybdenum, it's extremely high melting point. This is molybdenum, just imagine tantalum, that's very, very hard to transport, right? But also, even with that, their vapor pressures are quite low if you compare it to the chalcogen. And so a lot of times people have to use alternative sources, not pure elements. They have to use oxides of these transition metals, halides, but also carbonyls. And then a lot of times these days, some people can use organometallics like beta diketonates. So all of this is ultimately to get to sufficient vapor pressures or fluxes to actually grow these materials, okay, in a controllable manner. So this is a challenge. And so what I want to first start off with is talking about some of the crystal growth methods to grow some of these materials. And so I'm going to start off by talking about chemical vapor transport. So I'm sure that at this point you kind of understand what chemical vapor transport is, but just to review very quickly, so this is typically carried out in a sealed ampule, right? And ultimately what you need is to set up some temperature gradient, use a furnace to do that, but you need a transport agent. Ultimately, in this case, you need to be able to transport the transition metal, okay, from the hot to the cold region. And so typically the transport agents are iodine, bromine, and chlorine, and you can also use other transport agents as well, for example, the oxygen themselves. But these are the common transport agents used for most of the crystals that are grown today, are the ones that you can buy. And so there's a variety of resources to know, like different recipes to grow a variety of these transition metal dichlorogenides listed here. Here are some of the temperature in order the temperature profile that you would set up. Most of the time, you realize that these reactions that are happening by sophisticated chemistries to transport and ultimately react. And so one of the issues, obviously, is incorporation of these transport agents in these crystals, and that always is challenging to make these crystals very pure through these techniques. But they work very well, and you can get very large crystals. Ultimately, to use these processes, you first need to make these polycrystalline sources, and so you start off with high purity powders. You can use a Rotten furnace or just a normal furnace to crystallize, and you take that powder, you add your transport agent and so forth, and seal, and then set up your temperature gradient to grow these crystals by chemical vapor transport. But things that you should consider, specifically because you're dealing with high vapor pressure elements, sulfur and so forth, there are things that you need to consider in this process, okay? So generally, people prefer to use iodine because it's solid at room temperature. You can also use bromide, that's less common, but these two are the most. Chlorine is usually not used because it's gas and it can be quite toxic, and so you use alternative chlorine sources. And I'll show you examples of that. Things that you need to consider is obviously the vapor pressures of the sulfur solution fluids of the chalcogen. And so you want to be careful that you don't obviously explode your ampule. I've done that in the past. You can use simple ideal gas laws to calculate the pressure, and kind of getting a sense that a rule of thumb is less. Total vapor pressure of less than 6 atm, ultimately for a wall that is thick, like listed here. One thing you can do is to sort of anneal at the melting point first to make sure everything first vaporizes before you kind of proceed with this growth. So that's kind of the general rule of thumb to grow by CVT, and these are examples of crystals that you could grow by chemical vapor transport. But the best crystals today for these transition metal dichlorogenides, in terms of quality, is actually not grown by chemical vapor transport. It's actually grown by flux method. Yes.
So, how do you determine the concentration of transport agents?
How do you determine the quantity? Yes, that's a wonderful question. Yeah, I'm not sure. I mean, I think of it in terms of, well, you need to react that transport agent with the transition metal. If you have an excess, that's never a good thing. So I think that's what's dictating is that reaction rate. Now to quantify that, I have to think about it. I'm not sure I can answer that at this point. Yeah. Sorry.
That's a good
That's a good question.
question.
You know, a lot of this is also art too. Yes.
When you're using sulfur, you said that you're ramping, right? The temperature until you get and also dwell at the temperature. When you're doing say selenide or etc., would you also ramp the temperature low or like slowly, or this is only for that?
Yes, you should do that. Yeah, of course. But the vapor pressure of sulfur is quite high. That's the biggest problem.
So I guess my question is like, is the ramping only to avoid it, like avoid the ampule from shattering, or is it also helping like the crystal growth as well, like doing it slowly?
I think it's the first part. It's to not explode the ampule. The growth is happening at a higher temperature.
Okay.
Yeah. Okay. All right. Cool. All right. So just to continue, I was saying that flux-grown crystals are actually sort of the preferred for growing these high pure crystals. In fact, a lot of the work was done by Jim Hone at Columbia, showing that, for example, CBT grown as a diselenide versus flux grown, you can significantly reduce the point defect density. And actually, it turns out that this will be it's important in order to see some of these interesting physical effects. And so, although size is always the issue sometimes, but this is the preferred, but most of this is more at the research stage, so you couldn't like purchase flux grown crystals very easily. But this would be the better way. And I think Julia mentioned this review article. I thought that was really great on growth of van der Waals solids, but crystal bulk grown solids. And so I really recommend looking at this if you're interested in bulk growth.
That's a question.
Yes.
Is that an AFM image, right?
This is ST. Yeah, so you're looking at these little individual point defects. Yeah. So now that you have the bulk crystal, yes, sorry. Good head.
Yeah, really quick. So my prejudice is normally that flux growth will more commonly give inclusions and defects, but in this case you say it's the opposite. Is there any intuition on, is that actually unique, or is this very case by case?
So what's the reason? So I think the biggest issue with CBT grown crystals is that you're always deficient in the chalcogen, and somehow the flux grown crystals seem to reduce that. Now, why? I think maybe perhaps you're not depleting the sulfur in the process, or condensing it to other places. So maybe that's the reason. But this is that's a great question. From a fundamental mechanism, why would flux be better? That's my best guess. Okay, I saw one more hand. Yeah.
So since you mentioned deficiency, are the defects basically a more vacancy defect?
They're mostly chalcogen defects. Yeah. Okay, great. So then once you have your bulk crystal, now you need to exfoliate it, right? And so depending on the crystal, some can be very easy, some can be extremely hard to exfoliate by a variety of techniques. And so there's quite a nice paper that came out some years ago, kind of to quantify the exfoliable, or the how easy it is to exfoliate some of these materials. Obviously, things like graphene is very easy compared to some more exotic things like these topological insulators, this and that. And so it becomes challenging. But what are the techniques that are used to exfoliate? There are kind of mainly three. Lithium is just interpolation. Essentially, you can do this electrochemically. You can interpolate lithium, for example, then you just dunk it in water or just sonicate it. And the beauty of this technique is that you can actually get monolayers very well. Okay. Now, size is always a challenge doing chemical or liquid based exfoliation methods, but monolayers are very easy to achieve. You can also use organic solvents where you sort of disperse the crystal in organic solvent, you sonicate it, you choose some solvent or mixture in order to have some specific surface tension that you don't allow these crystals to agglomerate into clusters after you sonicate. You can also use surfactants, specifically acrylic in nature, where the hydrophobic head will sort of bind to the crystal, and hydrophilic will then allow you, once you sonicate, to separate these crystals. Today, people make inks out of them using this technique. You can also use things like ball milling as well to provide sufficient sharing and moving of the layers from apart. Okay, so lots of different ways to do this chemically, and in fact, people have been thinking about this quite even much longer than ago. So I always encourage students to go back to the literature to see how far you'll find the earliest observation. And so this is one of the first papers that show that you can exfoliate MOS2 using lithium interpolation. You know, it was before I was born. So, you know, I always like to look at these things, but in fact, you can do this through other techniques. And I talked about just simple mechanical exfoliation. You can use this by the Scotch tape method. And people did this all the way back in 1966. I mean, that's when I found this paper, I was very surprised that no one realized this. And so mechanical exfoliation is very simple, and it's actually anyone can do this at home. And simply, you just have to take your 3M Scotch tape, or whatever brand you prefer, and you essentially put it on the crystal, you kind of peel, and you can stamp and peel on PDMS stamps, ultimately to get to some thickness or number of layers that you desire. You can easily measure the thickness of the layers using atomic force microscopy, right? You can also stamp these layers on something like 90 to 300 nanometers of silicon dioxide silicon, and due to the optical contrast, you can calibrate the color, and ultimately then you can sort of know what number of layers you have. So you can do this very easily in any lab. So that's why people like it. You can also go a little beyond and actually use things like Raman spectroscopy. If it's a semiconductor, you can use photoluminescence to also find what is the layer number and so forth in these exfoliated layers. And then you can then stack these layers using a variety of techniques. And so there's lots of people doing this and create a variety of heterostructures. Okay, so this is what people do. And then you can stack, make twist angles. There's different ways of picking up. I'm not going to go through all of that today. But one fun thing I'll leave you with is if there's a group that wants to do this in an automated process using robotics and so forth to create kind of hundreds of layers of stacks. And so I thought this was kind of a fun paper that came out some years ago. So one of the first demonstration of stacking these individual layers to create a device, specifically creating a quantum well device, was actually done by Novoselov some years ago. So this was like the first stacked layer between different classes of these 2D materials, and people are making very exotic things today. Okay, so this is the one way to do this is through this top-down approach. Okay, but there's another way of doing this even easier than just exfoliating individual layers from bulk crystals, is to do something like metal transformation, and I'm going to talk about this next. But just to summarize, although you can grow these crystals, beautiful single crystals, it's actually not a very scalable process. Obviously, hopefully I'm not offending anyone by saying this, but this is one of the challenges in the field. Okay, so then what is metal transformation? It's very simple. You take a metal, you deposit it by some physical vapor deposition technique, and then you ultimately anneal that metal in the chalcogen environment. Very easy, right? Do this in a furnace. You can do something like soft chalcogenation. Essentially start off with a metal, you then have some sulfur selenium fluoride powder, you transport it, it converts it to TMX2, or you could do a solid state reaction where you deposit the chalcogen and the metal, and then you just heat it up, and then you have solid transformation. You can also do this, you don't have to use a furnace, you use a laser, you can do this with any kind of heating mechanism method. And you can actually make this on very large scales, okay? One of the challenges with this technique is that typically your grain size is very small, it's like oriented, usually it's polycrystalline. And so that also is a challenge to actually realize the variety of physical effects that I've talked about. And so usually this is not desired. And so this is something that you may find for other things, maybe in catalysis and so forth. So this is not very good. So then the other approach is using powders, and this is actually the most common in laboratories today. And so what essentially you do is you have a furnace, it can be single zone, it can be two zone, and you have sulfur as a powder, and you have typically you need a transition metal source like MO3 is a very common one. Then you have some substrates and you just flow some argon through, and then you basically transport the sulfur downstream, and then you have chemical reactions. Okay, so it's called powder vaporization. It is chemical vapor deposition, but with powders. And so this is essentially how this kind of works. And depending on the orientation of the substrate, you can change the way these crystals will grow onto the substrate. For example, if you have the substrate sort of facing up, you could have, obviously, if you have a sufficient entrance length, you establish lambda flow. But then when the gas flow is then interacting with the sample, you get turbulence, and then you can get vertical grown crystals. If you have a sample facing up, right, then you can have sort of like a plume where you have the source sort of spatially changing, and it's the source that's changing is the chalcogen, so you have depletion of the source, and then you can form sort of small crystals that's changing in size and shape. And then, obviously you can do all sorts of weird things and change the morphology of the film. But what I'd like to focus on more is on this one, E. And yes.
What's the flow rate of the argon?
Like 100 SCM, that range.
Time.
That, I guess that's slow for me, because for MOCVD it's like liters per minute. Yeah. So that is, I think the goal, what you want to do ultimately is just ensure laminar flow, right? So usually, you have easy way to do this is have a very long tube, a small diameter. So that's the key here. And what I'd like to then focus on is this slide. So I told you that you have this transition metal, high melting point, low vapor pressure, chalcogen, low melting point, high vapor pressure, and you're essentially, you can think about this is that the sulfur or whatever the chalcogen is sort of spatially changing because it's being consumed in the reaction. So you have some variation in the transition metal to chalcogen ratio spatially in this experiment. And so this ultimately not only dictates the size of the crystals that you would develop, but also the shape. Okay, so again, if you think about the sort of hexagonal nature of this crystal, if you are essentially in the regime where you're sulfur deficient, what happens is that the growth rate, so when you're sulfur deficient, you have more transition metals. And these transition metals are ultimately going to start to incorporate at the edges that are terminated sulfur. This ultimately makes the growth rate of the sulfur edges much faster. Then you end up with edges that are terminated with the transition metal, right? other way around, when you're sulfur rich, that's extra sulfur is going to interact with the transition metal edges. That's going to make that growth rate faster, and then you end up with edges that are sulfur terminated. And then obviously, if you're sort of in the right regime, then you get the sort of terminations of both the transition metal and the chalcogen. So you can actually see this in this figure here, where you see that, obviously closer to the sulfur source, you're sulfur rich, but then downstream, you're sulfur deficient, but then you still have these triangle shapes and the terminations become different. Okay, so this actually comes up a lot of times in a variety of systems from this class, just because of this ratio that can change of the shape. Okay, so another way to get around with the low vapor pressure of the transition metal is to essentially change it into something that has a high vapor pressure, especially niobium is one example that is very hard to transport. So what you can do is add some metal chlorides, even something like salt or KCl, whatever you like. And that basically creates a compound with a reduced melting point so that you can then sufficiently transport, because it'll have a much higher vapor pressure. And so this is something that a lot of times people do. Another thing about the powder vapor transport technique is that now you can not only grow monolayers of small little crystals, but you can sort of combine different sources to create junctions, and these junctions can be sort of out of plane, so you can have this, they're kind of stacked on top of each other, but also you can create these in-plane junctions just because you can sort of strategically place the source in a certain way. Or you can have sources on both sides of the furnace, and you can flow in one direction and then flow in the other direction, or you can have a sliding furnace. So there's also interesting tricks that you can play to create a variety of structures. So what is the challenge with this material is that obviously it's not uniform. As you can see, spatially it's changing. It's also not very scalable, right? You're kind of limited, but you can essentially do interesting physics and different studies like you would do simply with chemical vapor transport bulk crystals that are sort of fabricated from a top-down approach. So I'm gonna pause here. This is the midpoint. Is there any questions from any questions? Yes.
The very simple question, but when you're using the oxides or the chlorine or whatever, do you need to basically prime the stoichiometry so that it's the target phase? Does that make sense?
So I understood your first part. So you're saying, do I need to have the stoichiometry of the chalcogen to transition metal source be a certain way to then ultimately? Yeah, okay, so great question. So typically you grow in an excess, usually people want to grow in excess chalcogen, largely because it depletes through the process, and a lot of it gets sort of wasted downstream. So that's one reason. And usually you want to have a low transition metal. Ultimately, you can see that you want to grow monolayers at a time, right? And so you want to be able to really control the nucleation density. And so if you just kind of weigh them in the sense like 2 to 1, right? It doesn't actually grow high quality crystals. So you actually want very low, you actually want very high chalcogen to transition metal ratios in the thousands. Okay, so that's usually how you think about it, largely because of this vapor pressure issue. This is hard to control by the techniques that I just talked about, but can be controlled very well by the next set of slides I'm going to talk about, which will become clear.
Can I ask one more follow-up?
Yes,
And
please
that's,
go ahead.
so if you were targeting, let's say a binary, but there was multiple binaries in the system, so more than one phase, like maybe that's not the case for molybdenum ditelluride, but hypothetically,
Yeah.
is there any way that you can favor the target?
Yes, this is a great question. I actually didn't get to that towards the end. Yeah, that's a big challenge in this field, actually. Yes, I'll take your question.
So what's the substrate that you're using?
Oh, okay. So far, none of this is epitaxial. So it's actually silicon dioxide. It's like an amorphous surface. So you can do this on silicon dioxide because of the weak interaction between the layers and the surface. But you don't have any registry, no orientation control. And so it's hard to get films that are single crystal. They're all polycrystal.
So maybe in the case, in the previous case where you showed on this triangle, maybe it was substrate where the chemical structure was similar to whatever you're growing on it. Maybe can you get them to be the same?
Yes, you can control the orientation, which is then, yeah, I'm going to talk about that next. So I'm going to take your question. Go ahead.
Just follow up this question. I saw some papers they actually using like mica instead of the silicon dioxide. Yeah.
Yes, you can use mica, you can use graphene, and you can actually do epitaxy, use crystalline surfaces to orient things too. Yeah. So mica is good as well, depending on the grade of the mica, but that is another surface alternatively to SiO2. But SiO2 is very common actually. It works very well, just to grow individual crystals. Okay.
Quick question?
Yes.
I'm just trying to understand. So the powder is spread out on the substrate and then it's essentially all converted to film? Or?
No, it's all vaporizing. And then reactions are happening on the surface.
Okay.
Yeah. It's like CBD. Yeah. Okay. So I'm gonna talk about the next tab. I hope I have time. I'm gonna rush this. Not too much though. So I'm gonna talk about some of the common, I would say, scalable approaches, things that I do myself, which is CVD, and then answer your question about how do you control the phase, right? Obviously, and that's going to be very challenging for the system when you'll see the next slides. Okay, so CVD actually is sort of I would say the most preferred technique, but I will introduce what are the challenges with the physical vapor deposition techniques like MBE. And so what I'd like to review are some of basic fundamentals of epitaxy, because this is where this applies mostly today. So as you know, a material can sort of grow on a crystalline surface, and depending on the mismatch, you can then, and thickness, you can go from a layer that is sort of morphically strained, and then the layer will relax and then you can form dislocation and so forth. You don't have this issue with van der Waals surfaces, and so mismatch is kind of like relaxed in a sense. And then there's this idea of quasi van der Waals, which it means that you have a crystalline surface that has ultimately is going to dictate the rotation or the orientation of the crystal growing on top of it, which is van der Waals rotation. Okay. So this is what people like to refer as quasi van der Waals, not van der Waals growth or conventional epitaxy. And there are two things that one must think about in choosing a surface to grow material of this nature. One is sort of the rotation of the film with respect to the lattice of the substrate, right? So this is one thing you want to think about, but also how over some multiple unit cells, the commensability of this two-dimensional layer is related to the crystalline surface. Ultimately, this will dictate what is the lattice mismatch, and if there are different rotations in which this mismatch is sort of degenerated. Okay, so for doing epitaxy, if you review the literature, a lot of times people like to use sapphire largely because it's widely available in bulk crystals, and people slice them up into substrates. And so if you look at the lattice mismatch, so 3x3 unit of MOS2 over 2x2 of aluminum oxides at the 001 direction surface, the mismatch is quite low, it's like 0.4 degrees. But then there are substrates like gallium nitride actually that are actually much lower lattice mismatch. So you can actually get very nice oriented crystals growing on the surface. Here's an example of MOS2 monolayer grown on sapphire by CVD, very large domains, are oriented. Here's gallium nitride, same deal. They're sort of oriented. But what you'll realize here is that there's 2 rotations, right? It's kind of interesting, right? That's actually a bad thing. They're degenerate, and you need to somehow break this degeneracy, right? Why you would need to break this degeneracy is the following, right? So this 0-60-degree rotation of these domains, you can imagine that when they come together, when they coalesce, right? So nucleate grow, coalesce these monolayers to form these inversion domains. Physicists love them because they have interesting transport properties. But if you're thinking about creating a very large scale film that is consistent, this is actually a problem. So somehow you need to break the degeneracy and be able to have all these different triangles or whatever the shape ends up being, or rotate oriented in the same direction to get to a single crystal like the bulk crystals you would grow by the other techniques, right? So choosing substrates to do this is something that you must consider. So what is the status of the field in the first part with molecular beam epitaxy, or just generally these physical vapor deposition techniques? I personally do not do MPE. A lot of people do, but what are some of the challenges? Okay, so just to think about MPE from sort of the components in a reactor. Usually this is happening at ultra high vacuum. So something like 10 to the minus 10 bar, right? So you have in order to have the mean-free path sufficient to have this molecular beam from the K cell and so forth, right? So it turns out this high background pressure is actually a problem for synthesis of these transition metal dichalcogenides, because remember that the chalcogen has extremely high vapor pressure, right? So now if you have this extremely low vacuum and you try to pump in something like sulfur, right? First thing, your reactor is going to be sulfur forever, but you can't actually have sufficient sulfur impinging onto the surface to participate in the reaction. And so this is a challenge because not only that the sulfur has a high vapor pressure, you need sufficient temperature to drive the fusion of the transition metal, which these have extremely high melting points, so you can't be at like 300 Celsius to grow the best single crystal films, right? You need to be at high temperature. And so now you have a temperature limitation and also a source limitation. Usually you can't grow sulfur-containing compounds by MBE. And so because you have to be at low temperature in order to not sublime all the chalcogen, you actually form crystals with high point defect density and low grain size. So I'll show you this here. So this is an example of MOSC2, tungsten diselenide, grown on epitaxial graphene, just the chosen substrate. And you'll notice here from what we've seen before, the grain size, the domain size is quite small, right? Because they're at low temperature, there's not enough energy to provide sufficient diffusion and ultimately grow nice crystals. So this is the status of the field. It's actually, you can grow some of these chalcogenides, but you can't get to this very beautiful, high crystalline quality, low, large grain size films. So this is the challenge. There are some, things that people are playing around with, but this is still remains a big issue. And if you look here, growing something like tantalum disulfide is actually very challenging. You have to either do this by E-beam, and even by E-beam, you won't have sufficient fluxes to actually grow these crystals very well. So actually, people can grow this in a really systematic way, and maybe this is something you can maybe do as a project in the future. So this is the issue. Okay, so now I'm just going to focus on MOCVD and CVD techniques. So an MOCVD reactor looks something like this. It's sort of a basic schematic. So what's interesting about CVD by MOCVD is that the sources are outside the furnace, right? They're not inside the tube furnace, but sort of outside in bubblers. And typically they're liquid or solid, metal organics. They can also be carbonyls. And you can also combine this with other gas sources like hydrides. And so you can use something like hydrogen sulfide as a sulfur source, or hydrogen selenide as a selenium source, which are just, so hydrogen selenide is very toxic, by the way. The beauty about an MOCVD reactor is that you can inject a precursor in and out in a steady state fashion through these run vent assemblies. You can choose different reactor geometries. You can choose different chamber wall temperatures. You can have hot wall versus cold wall, which can control gas phase supersaturation. And then you can use, usually use a very, kind of cheaper pump, so you don't have to be a UHV. And so typically pressures are operating in the reactor in a millitorr to sort of atmospheric, and sometimes at high pressures in very moving systems. But ultimately, the key is, if you ever did MOCVD, please, realize that these things are extremely toxic, fluoric, and so forth. And so you must be closest in a ventilated enclosure with the correct detection. So, just don't do this at home. And so the first actually paper that has shown that you can use MOCVD to grow monolayer MOS2 was in 2015 from Jiwon Park's group by Kibong Kang. And essentially they used, metal organics like the methyl sulfur and molybdenum hexacarbonyls, and to grow this monolayer on a very large wafer. And the key to control nucleation is to have sort of this low gas phase supersaturation, and they do this by being at very low pressures, at least 10 to the -3 torr. So by doing this, unfortunately, the growth rates are very long, right? So the reason why you don't want to have, you want to reduce the gas phase supersaturation is that you want to grow, one layer at a time and not grow a bilayer on top, right? As you're growing the monolayer. So it's very different than growing a thin film like gallium arsenide. It's, it's very, you're dealing with one of, few layers of atoms at a time. So this is kind of the big challenge. So to increase the growth rate, obviously you want to go and change the geometry of the reactor. So this is a hot wall reactor, and so they want to reduce supersaturation. And the reason a lot of this is happening, you have reactions that are happening in the gas phase because the temperature at the furnace is heating up gas. So you can get around this by using a cold wall reactor geometry, and this is an example of this. So you can cool the walls with water or some other liquid, and you can heat locally the crucible using induction heating, right? So it's just a simple schematic of this. And you can use a variety of other metal organics that will ultimately you won't have this reaction happening on the walls. Okay. So I'm just going to give you an example, which I think is one of the best examples of showing growing a monolayer of tungsten diselenide. So the first step is the nucleation step, right? So what you need to, in this case, is you need to have sufficient partial pressure to nucleate on the surface. Then you can do a step called ripening, where you expose the surface to the chalcogen source, which essentially will consume all of the transition metal on the surface to form very nice domains. And then what you then want to do is to lower the partial pressure to reduce supersaturation and ultimately grow laterally out these crystals to form monolayers as opposed to bilayers of these crystals over time. So as you can see, this only took roughly 45 minutes to grow a monolayer. In this case, it's on sapphire versus 1 day. And so there's lots of improvements in this field. And it turns out that you have the same issues that I talked about in the powder in terms of the domain shape. So here's just a series of SEM images as a function of temperature from 600 to 900 C. So what I'd like you to show you here is that this is just a figure showing that temperature range, but here plotted on the left is the domain size and then the density of the domains. And you'll see between 700 and 900 C is that the domain size and density is not changing, right? So this means that this is a mass transport limited growth, and what's being mass transport limited here is tungsten to the source, tungsten precursor to the surface. But what you'll notice here is as you go from 700 to 900 C is that you have these triangles that become truncated, right? And so what is the reason here? Again, is you increase temperature, you're depleting the chalcogen surface that's changing the transition metal to chalcogen ratio, changing the growth rates of the facets and ultimately changing the shape. And so usually you have to grow at an extremely high chalcogen transition metal ratios in the thousands in order to really control the shape of the domains. Okay. And so once you are at the right shape, you can then kind of grow this over time and really reduce the bilayer coverage. And so if you'd like more information, I really encourage you to look at this paper by one of my former postdocs. But then what I'd like to show you next is how do you break the degeneracy, right? So here's an example of growth of tungsten diselenide on hexagonal boron nitride. And what you'll notice immediately in these images is all these triangles are oriented in the same direction, right? That's a good thing, right? Because now when they actually coalesce, you won't have these inversion domains between them. And so this, so you don't have some weird transport that's happening at the interface. And the reason why you can do this really is because the defects in the boron nitride act as nucleation sites, and it also breaks the degeneracy such that all the domains are now oriented. So you can think about this defect as sort of like a glue, right? It's like orienting all the layers in a specific direction. So one can essentially use defects to control an orientation of these crystals. Okay. So just to summarize this part, you know, things that you want to consider when making these materials by epitaxy, you need to consider substrate, orientation of nuclei, and so forth, sufficient energy to drive diffusion, but not too high, because then you deplete the chalcogen source. So then you have to be a high transitional, high chalcogen to transitional ratio. But also you need to control lateral growth versus vertical growth, and so you have to be, you know, control the supersaturation and so forth. And so this is where the, you know, some of the things that you need to think about if you're working in this area. But people have actually made a lot of interesting kind of systems and heterostructures using MOCVD. Here's just an example from David Buller's group, June Park, showing that you can create lateral heterojunctions between different materials simply by changing in and out the precursor. But I think the most striking example actually came out last year, which I thought this was some of the best results. Here you're seeing a cross-section TEM of individual layers grown by MOCVD. And so you have like moly disulfide, tungsten disulfide, literally one layer at a time. I think I've never seen this by any other technique that you can do this. And so this, you know, still a lot of development in this field, but a lot of room, you know, lots of things are happening, at least in making heterostructures. So do I still have 5 minutes or I have to, because we
2 minutes.
2 minutes. Okay, so then if I have 2 minutes, I'm not going to answer the question about phase control. And I'm just going to go to the summary and take questions then. So, oh man, where's my mouse? Yeah. So I'm just going to summarize and then talk about how you control phase in this system. So, you know, lots of interesting things are happening in MOCVD ground samples, less in MDE unless you can get around the temperature issue. And so I see that this is going to be the key moving forward in this field. Now, to answer your question about phase control, a lot of the work to do this actually is being done by doping. So you can control the phase post growth by interpolating elements that will essentially provide sufficient charge density to transform it, or you can look at the phase diagram, you know, quench that phase out. But in thin films, it's very hard to do that, right? You can't just quench a film from a CVD reactor. And so a lot of times what people are doing today is actually adding dopants, and the dopants can not only change which phase, which form, but also change the stacking and so forth. So it's lots of effort in this field, and you know, at least it looks very promising, but it's not very scalable yet. So with that, I'd like to take any last questions, and you know, if you would like to get these slides, or you know, please let me know. And so if there's any questions, please.
Okay, say thanks. We'll also say that the plan is to post the video and slides online.
Oh, okay, great.
After this.
Yes, yeah. Any questions? Yes.
Could you go back to the AFM where you're showing the different stages of the growth?
Yes. This here?
Yeah. So in the right one, why do we see step edges? Like not the trunk part?
This step edges, this is the sapphire step edge. Yeah. Yes.
But you can't see it in the earlier AFMs?
Yeah, so what happens is as you, you know, you start off with a surface that looks like this, over time, you know, you're annealing the sapphire, right? And so the sapphire is also sort of, you know, you have steps that are forming, and you also have step bunching and mandering that also is happening on the surface. So that's why that's happening. And so sometimes what people do is just anneal the sapphire first, get all the steps in, then do the growth. It turns out the step edges can also be points of nucleation, so you can get step flow growth from the step edge to the terraces. So that's another way to go about this, but that is a step edge. Yes.
I think at the beginning you showed that there are polymorphs that are different types of stacking order. Has there been work in heterostructures to mimic that, and then their properties in that?
Oh, so how to make a heterostructure that mimics the polymorph? Yeah. You know, so doing it by bottom up is very challenging, and I talked about doping as a way to do that. You know, at least today, there's some observations. You dope rhenium into molybdisulfide, you can go from the H2H stacking to the 3R stacking. So, so that's possible in thick layers. But to exfoliate and then create these stacking orders, they're very challenging. You know, even things like twisted layers, a little bit of temperature will actually, which, you know, these layers will slide back to some, you know, equilibrium, you know, position. So it's hard to artificially make these very different stacks. Yeah, there is, I think, I don't know if there is any other way of doing it unless you do it through a bottom-up technique. Yeah. Other questions? Yes.
Do the sapphire step edges affect the properties of your dichochalcogene?
Yes. Actually, sapphire is a terrible substrate in that sense, because you have these, you know, modulations on the surface that constrain the layer, and that turns out to change the optical properties or the electrical properties. So usually you want a flat surface, like boron nitride. So actually boron nitride is a great substrate to grow these crystals. But you know, these steps at the scale, right, these monolayers, they can really affect the properties. So yeah, that's an excellent question. You know, this is more questions than in my class. So I'm like super happy about this. Yeah. Oh,
Keep going.
okay.
So are the layers thick enough where if you do X-ray characterization on there, you get signal from the sapphire substrate too?
Yes, so you can do X-ray. You have to orient this in plane, and then you can actually do X-ray diffraction in a very basic four circle geometry. Yeah, so X-ray is definitely used in these epitaxial layers. Yeah. Yes.
Can you monitor these nucleation, the ripening and growth stage in situ?
Yes, actually, that's my part of what I do in my lab. So you can use reflectance measurements or things like ellipsometry, these kind of light reflecting on the surface to understand the growth in a CVD environment. You can also monitor some of these exotonic features in reflection. Specifically, some of them are quite bright even at high temperatures. As a probe to understand strain and number of layers. In NBE growth, you can do things like read and you're at ultra vacuum, so you can use guns and things like that. So it's very early on in this field, like developing optical probes to probe monolayers is not easy. And understanding what you're seeing, that's the other question. Like you see all these wiggling lines, what do they actually mean? And so we're very, very early on in this field of in situ monitoring of these materials, but at least this is what people are doing so far. Great question. I see one asking.
This is a naive question. So, follow up on the sapphire step edge thing did you do any pre-treatment onto the sapphire?
Yes. So there's sapphire, you can pre-anneal it, and then you can clean it. Get to move any organics on the surface. So that's usually the prep. So some people don't like to pre-anneal the sapphire, and they want it flat and try to reduce the step edges that form, but they're always going to form. Same thing like silicon carbide, you have that same issue. So the treatments are usually thermal heating at some temperature in a box furnace. But it turns out the steps are definitely an issue.
And I'm wondering, if polishing could make it smooth? I don't know.
Oh, I see. Yeah, so typically these substrates are polished. And their dyes are polished and remove all the surface defects and things like that. It's just what happens when you heat it up, you form steps, and those steps are moving and interacting with each other. And so that's hard to control unless you control the temperature in such a way so that they don't form. Yeah, so that is the main issue. Going to something like mica, someone mentioned mica. Actually, you won't get that effect. Graphene is a great substrate, or nitride, you won't have these steps that form. The problem with things like graphene is rotation. Orientation is not always easy to control. But boron nitride, why it works is because you have defects that can pin the domain so that you can fix the rotation to actually coalesce into a single crystal. So there's still a lot of engineering that must be done. It's still very early, I think. Lots to learn, but that's the field currently. Any other questions? Yes. Is it okay? I take more questions.
Yeah, one more, and then I have a question.
Okay, great. Yeah. Go ahead.
With there's a lot of materials these days, like I'm thinking of ruthenium chloride or these cesium, vanadium, hydrogen superconductors. They're very thin and bend easily. When you bend them, that just ruins a lot of properties. Are you ever concerned that when you just pick things up with the Scotch tape, there's a lot of bending and twisting, especially with thin layers?
Yeah, I did a lot of exfoliation as a postdoc, actually. The worst thing is when you put the heterostructure together, it wrinkles, and then you can't actually. Well, firstly, you won't know where your layers are, but actually all of the strain can change the properties. So that is always a concern. IMAC in Belgium, right? They are transferring these 8-inch wafers of MOS2 now. And they worry about the transfer process where you want it to be flat. So it's hard, yeah. So, physicists, they're very good at making these heterostructures, but very at small scale, right? Where they can really control this issue of strain and things like that. one thing you can do is do these post anneal just to kind of iron out the landscape. That is an issue with transfer, absolutely. So this is why I feel from a technological sense moving forward, bottom-up techniques are the way to go, similar to what people do for the 3.5s and so forth. But yeah, absolutely, that is an issue. Yeah. But one could try to play tricks to control it.
So just since everyone here is going to become a faculty member at some point,
That's great.
can you give us an idea of the cost of a MOCVD setup?
Oh,
or
yeah.
MBD or
Yeah,
roughly speaking?
that's a great question. Actually, a few years ago, all these semiconductor companies were going out of business. So that's where I got a lot of my equipment, actually. But now all of a sudden, semiconductors are another, all these factories are open. Yeah, so an MOCVD reactor, if you buy a commercial one, you're looking at an investment of like $800,000, right? But if you're only interested in the science, you can actually build them, these small reactors to grow these materials with like $2,000 maximum. I think the highest cost is a pump, right? Usually, it's a new pump that is $2,000. If it's a refurbished pump. So I think it depends on what you're trying to do. If you're trying to scale, then it becomes very expensive. But if you're interested in the science, you don't have to scale, right? Actually, I have a mixture of these things going on in my group. So if you decide to go and become a faculty, always go for the high-end startup first, and then they'll always start high because you never get what you want.
Save your money.
Yeah, but that's an interesting question. Yeah, I think home built reactors. Actually, the first paper in 2015 by Kibam Kang, he grew this on 4-inch. It was a home built reactor in a fume hood, and it basically changed the field and the game. And so I think the science sometimes is more important than using sophisticated tools to make them. Okay, so
yeah, we should wrap it up.
so thank you very much for your questions, and